Today we are going to discuss the three-dimensional force system. As far as the three-dimensional force system is concerned, we have already seen the planar equilibrium of a rigid body, planar equilibrium of a particle, wherein we were talking about the summation of forces along x-axis and summation of force along y-axis has to be equal to zero for the equilibrium of a particle along x and y axis. That was a two-dimensional force system, we can say, and we can say that that was a planar equilibrium of a particle. Now sometimes we may be having a particle in space, okay, whose coordinates will be along x, along y, and along z direction, and the components of forces will also be along x, y, and z direction. So when we have force acting in space, when we have the force having three components, x, y, and z component of the force, and the force is in it's acting in space, okay. So at that time it's necessary for us that for the equilibrium of a particle, the summation of the force along x-axis should be zero, the summation of force along y-axis should be zero, and the summation of force along z-axis should be equal zero. So this is what we call as we have a three-dimensional force system, okay. So for a three-dimensional force system, for the equilibrium of a particle in three-dimensional force system, the summation of forces along x, along y, and along z direction should be equal to zero. Okay. Say for example, let's take an example of the equilibrium of a particle in three dimension. We have a question from our textbook which says, determine the force in each cable used to support the 40-pound crate. So we are having a 40-pound crate. Okay. This 40-pound crate is tied to cords. We have cord AC, we have cord AB, and we have cord AD. So we have to find how much is the force or the tension in the cord AD, how much is the force or tension in the cord AB, and similarly, how much is the tension in the cord AC. In order to do this question, first of all, look at the points. Look at the point B. If you look at point B, the point B is a point which is whose x coordinate is -3, whose y coordinate is -4, and whose z coordinate is 8. So if you look at this point B, the coordinates of point B are, we are having the coordinates of point B are along x-axis, it's -3. So it is -3 along x-axis. And as far as the y-axis is concerned, it's along y-axis, you have to move along -y-axis, so its coordinate is -4. And as far as the z coordinate is concerned, the z coordinate is 8 feet, okay. So these are the coordinates of this point B. Similarly, if you look at the point C, the x coordinate of point C is again, the x coordinate of point C is -3. So it's -3. Again, -3 is the x coordinate of, uh, not -3 actually. So sorry, the the x coordinate is, yes, the x coordinate is again -3. The x coordinate is -3. As far as the y coordinate is concerned, the y coordinate is 4, +4. And as far as the z coordinate is concerned, the z coordinate is again 8. Okay. So -3 feet, 4 feet, and 8 feet are the coordinates of this point C. What are the coordinates of this point A? The coordinates of point A are 0, 0, and 0. So this is our origin of x, y, and z axis. And as far as the point D is concerned, look at the coordinates of the point D along x-axis. See how much it is along x-axis and how much it's along y-axis, how much z-axis. So if you look at this point D along x-axis, the point D is on the x-axis. So it's having only x coordinate, and y and z coordinates uh, are equal to 0. Okay. Now the force of this crate is 40 pounds, and this force will be acting downwards. So this will be a force of 40 pounds. Okay. So we are having 40-pound force acting downwards. Now in the cord AB, there will be tension developed in the cord AB. So let's call that as tension or force. We will call that as the force developed in AB is equal FAB. Okay. So this is the force developed in AB, and we will be having force developed in AC. Let's call that as the force FAC or the tension FAC, and we also have the force developed in the chord AD. Let's call that as FAD. Okay, so these are all vector quantities. So we have, this is our vector, so this will be a vector, this is also vector, and this is also vector, and we know the entire system is at equilibrium. Let's write the equilibrium equations for point A. Now see, for the equilibrium uh, of this of the particle uh, at point A, or the equilibrium at any point, we'll write summation of all the forces should be equal, summation of all the forces, the resultant of all the forces should be equal to zero at the point where you are actually writing the equilibrium equations. So let's write the equilibrium equations for all the forces that are acting. So once we write summation of all forces should be equal to zero, it means FAB plus, this is one force, and we have FAC, and FAD, force FAC, and we have FAD, so plus FAD, vector FAD, and we are having this 40-pound force. This is acting downwards along minus pi. So let's, uh, so right, this will be written as minus 40 k cap. Okay, should be equal to zero. This is our equilibrium equation. Okay, the summation of all the forces is equal to zero. Now let's write this FAB in terms of its coordinates, in terms of its components along x, y, and z, AC in terms of its components along x, y, and z, and FAD in terms of its components. So if we went on to write this FAB, look at this FAB. FAB is the force acting from point A towards point B. So we can write this FAB as, FAB can simply be written as FAB, force FAB can be written as magnitude of force FAB. Force FAB is a vector. Vector FAB can be written as magnitude of FAB along a unit vector drawn from A to B. So we'll be having, we will write a unit vector. We have to write a unit vector from A to B. Let's write that unit vector RAB cap. So RAB cap represents a unit vector from A to B. So we know this FAB is a vector quantity. It will have magnitude equal to FAB, and it's acting in a direction from A to B. So if we multiply the magnitude FAB by a unit vector from A to B, we will get the FAB vector. Now look at this RAB vector. RAB is a unit vector from A to B. Now how can we write this unit vector from A to B? We can simply make use of the distance formula. We can write RAB vector, RAB unit vector can be written in terms of distance formula as, first we'll write x coordinate of point B minus x coordinate of point A plus y coordinate of point B minus y coordinate of point A plus uh, z component of point B minus z component of point A, whole divided by the magnitude of the vector. That is, we can write down a vector from A to B. We know a vector from A to B can be written as its components having -3 along x-axis, -4 along y-axis, and 8 along z-axis. Dividing by the total magnitude will give us the unit vector from A to B. So we can write the unit vector from A to B. This can be written as -3 -0, x component of point B minus x component of point A along I cap. So this is unit vector along x-axis plus y component of point B minus y component of point A, that is -4 -0 j cap, z component of point B minus z component of point C, that is plus 8 -0, 8 -0, this along z axis, this is k cap. This is the vector from A to B, whole divided by the magnitude of this vector. The magnitude of this vector is minus 3 minus 0 whole square, that's minus 3 square, plus, this is how we write the distance between the 2 points in terms of the distance formula. That's minus 4 square plus 8 square plus 8 square. Okay, so this represents the unit vector from A to B. Similarly, we will write the unit vector from A to C and the unit vector from A to D. So it means, as far as this unit vector is now concerned, as far as the force FAC is concerned, we can write this FAB as, therefore we can write, therefore let's write it here. Let me rub this much. Therefore we can write this as, therefore we can write, therefore we can write our FAB. Therefore FAB vector can be written as, FAB vector is equal to magnitude FAB, magnitude of FAB, and uh, minus 3 I cap minus 4 j cap plus 8 k cap divided by each term divided by this number. Okay, so that will be minus 0. If you perform 3 divided by this much, that comes out equal to minus 0.318. That's minus 0.318 I cap. And then we have minus 4 divided by this term, that's equal to minus 0.424. That's minus 0.4 0.424. Okay, minus 0.424 j cap. And the last term we have, it's 8 divided by this term, it is 0.848. So we will be having plus 0.848. Let me write it here, plus 0.848 k cap will be writing here. So it's plus 0.848 k cap. Okay, 0.848 k cap is here. Okay, so this is our FAB. Similarly, we will write our FAC. Okay, so now we can write this FAC as, if we have to write this FAC, what are the components of C point? Minus 3, 4, and 8. Okay, these are the components of C. Then FAC vector, therefore, vector FAC can be written as magnitude of FAC, that is FAC, magnitude FAC, and the unit vector from A to C, that is x component of this minus x component of this. I will directly write that is minus 3 I cap plus 4 j cap and plus 8 k cap divided by the magnitude of this vector. The magnitude of this vector is under root of minus 3 square plus 4 square plus 8 square. Okay, that's equal to, therefore FAC vector comes out equal to, FAC becomes equal to magnitude of FAC. Then we have minus 3 divided by this much. Okay, that's again minus, that's minus 0.318 minus 0.318 I cap, and then you have 4 divided by this term, that is plus 0.424 j cap, and we have the last term, that is 8 divided by this much, that is 0.848 k cap. So this is plus 0.848 k cap. Okay, so this is our FAC, this is our FAB. So we'll be just highlighting them. So this is our FAB and this is our FAC. Now we have to talk about this FAD. Now look at this FAD. This is quite simple. FAD can simply be written as vector FAD, vector FAD, sorry, vector FAD is equal to magnitude of FAD. And in which direction is this FAD acting? This FAD is acting along x-axis. So we'll write this as I cap. It has no component along y and z axis. Okay. And we have the weight of this, the weight is equal, the weight of this crate is equal 40 pounds. This is acting along minus z axis. So it will be minus 40 k cap. Okay, where I, J, and K are the unit vectors along X, Y, and Z axis. So these are our forces. This is our FAB, this is our FAC, and this is FAD, this is W. Now write down the equilibrium equation. Summation of all the forces should be equal 0. That is, once we went on to write down the equilibrium equation, therefore we know, let's write down the equilibrium equations. Let's recall our equilibrium equation that we have just written. The equilibrium equation says FAC or FAB plus FAC, FAB plus FAC, and plus, this is FAC, plus FAD, plus FAD, and this weight component plus W should be equal to 0. This is what the equilibrium in 3 dimensions states. Now look at this FAB, substitute the value of FAB, substitute the value of FAC, substitute the value of FAD in this equation. So we can write, as far as this FAB is concerned, uh, as far as this FAB, FAC, FAD is concerned, let me add it up here. So we have, we have to add up this FAB to this FAC, or to this FAC, to this FAD, and this W. Now let's add up their I components. So we have FAB 0.318 I cap minus FAC minus 0.318 I cap plus FAD I cap. So this will be our I components. We'll separate the I components here. So we can write, let me write it here. So let me write it here. Let's write these, add up these terms. Let us write FAB. So you will be having, will be first of all having this minus 0.318 FAB minus 0.318 FAB minus 0.318 FAB. Then we have minus 0.318 FAC minus 0.318 FAC minus 0.318 FAC. This is our second component. And the third component along I, we have FAD, that is plus FAD. And all these components are along I-axis. So this will be 0.318. All these components are along x-axis. So we'll write them as I cap. Okay. So we have, these are I components we have written first. Then we'll be adding up the J components. So as far as the J component is concerned, it is minus 0.424 FAB. So we'll write down minus 0.424 FAB minus 0.424 FAB. Then we have second plus 0.424 FAC plus 0.424 FAC. Okay. And do we have any component? So we have taken the J component from here. We have taken J component from here. Do we have J component from these? No, we do not have. So we'll be having, we have no other J component. Okay. So this entire term, this is the components along y-axis. Plus the last components will be adding up the components along the z-axis. So we have plus 0.484 FAB. So we'll write is 0.848, 0.848 FAB, 0.484 FAB, 0.848 FAB plus 0.848 FAC plus 0.848 FAC, and the last component we have along K, it's minus 40. Okay, so this is minus 40, and all these components along z-axis. Okay, and for equilibrium, the summation has to be equal to 0. Therefore, we write, this is the equation for uh, this is the equation for equilibrium along three dimensions. Now individually, since we have the components, this when we have vector having components along x, y, and z with the with the right hand side equal to 0, so it's quite evident that the component along x-axis should be 0, the component along y-axis should be 0, and the components along z-axis should be 0, because this can be written as this is 0 I cap plus 0 j cap plus 0 k cap. This is how we write it. Since the two vectors are equal, then their x and y components and j components should be equal. The x component on right side should be equal to x components on the left side. The y components on the right side should be equal to y components on the left side, so on about the z components. So look at this equation. So we can write that 0 minus 0.318 FAB, this is equal to 0, this is equal to 0, and this is equal to 0. So from this equation, look at this term, just highlight this term, j component. So we can write minus 0.424 minus 0.424 FAB minus 0.424 FAB plus 0.424 FAC plus 0.424 FAC is equal to 0. Okay, FAC is equal to 0, j components. So once you solve this equation, you will get FAB is equal to FAC. So from this equation, we are getting FAB equal to FAC. So from this equation, we have obtained FAB equal FAC. Now substitute the value of FAB equal to FAC in this equation. Okay, so when FAB is equal to FAC, now we substitute FAB equal to FAC in rest of the equations and obtain the values of other components. Okay, so this is quite evident now. So if we substitute FAB equal to FAC, so we have minus 0.318 FAB minus 0.318 FAC. FAB is equal to FAC. So in place of this FAC, we can write FAB. Okay, so we have minus 0.318 FAB minus 0.318 FAB plus FAD is equal to 0, because I components are also equal to 0. So we can write from, once we use this equation, we can simply write 0.318 FAB 0. So that is 0. Minus 0. That's minus 0.628 minus 0.628 FAB minus 0.628 FAB plus FAD plus FAD is equal to 0. So this equation we have obtained from this equation. Now FAB and FAC, from this equation, FAB and FAC are same. FAB is equal to FAC. So we have 0.848 FAB plus 0.848 FAC minus 40 equal to 0. Okay. So from these two equations, we can substitute FAB in place of FAB. You can write now here FAC. So it is 0.848 FAB plus 0.848 FAC. So it will be 1 point, this is 16.9. So this is 696, 1.696 FAB minus 40 equal to 0. So 1.696 FAB becomes equal to 40 pounds. So from here we can obtain the value of FAB. The FAB comes out equal to 40 divided by 1.696. So we can easily find out the value of, so from this equation we can find out the value of this FAB. FAB will be 40 divided by 1.696 pounds. So once we have found the value of FAB, substitute the value of FAB here, we'll obtain the value of FAD. So on solving, we have obtained the value of FAB, we have obtained the value of FAC, as well as we have obtained the value of FAD. The forces that are acting in the chord AB, in the chord AC, and in the chord AD. This is how we'll be solving the questions based on the three-dimensional force systems. Okay, thank you.